in a static problem, what quantities are concerned? Well, the system is not moving. This is chapter 12. Chapter 12, Statics and Equilibrium. So when you have a system like a ladder against the wall, or you have a platform leaning against the wall with a string, these are all good examples of statics problems, right? So what you're going to do is sum of the forces on the system in the x direction is 0, sum of the forces in the y direction is 0, and sum of the torques about any pivot point must also be 0 if if the system is in equilibrium, right?
You're saying all those have to be 0?
Yeah, because it's not moving. Statics problems means
Okay.
the system is in equilibrium.
So these kind of problems would ignore like the normal force and the force of gravity?
Yeah. No, the force of gravity comes into play.
Oh, but they cancel out and equal 0. The normal force.
This is one example. Of course, there's lots of
minutes
them.
or less, maybe a little more. We're going to go over a problem involving static equilibrium. This is kind of a long problem, so let's get started.
This is a good example.
We have a step-by-step sine sign, which has a mass of 18 kilograms, supported by this cable, which makes an angle of 35 degrees with this beam. The beam has a length of 2.1 meters and has a mass of 25 kilograms and is supported by this wall. By the cable, comes down this way, supports the sign. The beam is attached to the wall.
Okay, so let's write that down. It's like the one that I just drew. Okay. What's the mass of the beam? 25 kilograms. Then the tension in the string. Right, we got a hanging weight here. And the hanging weight is 18 kilograms, right? It's the mass of the sign. Then you have, this is given, 35. And that's all that's given, right? And they're probably gonna ask you for what's the force of the hinge, what's the tension in the string, right? Those are all the unknowns.
At this hinge, and we want to know what's the force of tension in the cable, and we want to know what is the force from the hinge. Okay, now this problem involves static equilibrium. Static because nothing's moving, equilibrium because all the forces, when you sum them up, will be equal to 0. So we're going to, and this problem has torques, so we're going to sum up the torques and set them equal to 0. Sum up the forces in the x direction, set them equal to 0, and sum up the forces in the y direction, set them equal to 0.
He's talking a bit fast, huh?
There's a lot of stuff in this problem. You got to keep track of it. You got to think about it. I think it's best to go step by step. Step 1, I would say, is to draw in all the forces. You got to sum them up. Let's draw them in. There is the weight of the sign. There is the weight of the beam, which I put right in the middle of the beam. There is the tension force from the cable, and there is the force from the hinge.
Okay, so you are writing all the forces on the beam. The beam is our object, all the possible forces on the beam, right? So there's a tension here, so let's write the beam separately. The tension like this, the weight of the beam, and the weight of the sign, big mg, let's call it. Then the hinge is exerting a force this way. Now you might say, can't the hinge exert a force just horizontal? Why does it have to be at an angle? You know what? It could be horizontal. It could be at an angle up, or it could even be down. It probably depends on what the tension is and what the weights of the hanging things are. But most likely it's either horizontal or up. Down is hard to see, you know. In other words, the hinge is whatever you're supporting the beam on this end. It could be a screw into the wall, or it could be some kind of a hinge, like an actual hinge, you know. Okay, so then you're gonna do some of the forces in the x direction. So what are they gonna do? This is gonna be the force of the hinge. So they're gonna probably define an angle theta, right? And an angle alpha. So you can say F cosine theta, which is this force, is equal to what? T cosine alpha, right? Then they're gonna say F sine theta plus T sine alpha is equal to mg plus mg. Does this give you hope? Chapter 12 is easier? See, after you've seen what we've just seen, these don't look scary. Let's see what they do.
Just pushing back. Those are the four forces. Now we got to sum up the x and the y components, so that means we got to break these into the tension force and the hinge force into their x and y components, because they're not acting in the x and y components. So the next step is to break them down. So ftx is that component. This component is fty, the two x and the y components of the tension force, and then we have the x component of the hinge force and the x component, the y component of the hinge force. We've drawn in all the forces, we broke the tension and the hinge force into their x and y components, and now we can sum them up. Now I want to point out, before we do that, we want to find the tension force. We want to find the force from the hinge. We have these four components. This is really what we're trying to figure out. The y component, the x component, the x component, and the y component. We're going to find these, and then use the Pythagorean theorem and some trig to solve for the actual tension forces. So these are the four things, 1, 2, 3, 4, that we're really trying to solve for, because we're solving for the components. We broke those into their components. The tension force, the torques. There are 3 torques, okay? There's the torque from this force, there's the torque from the weight of the sign, and there's the torque, the rotation force from the weight of the beam. I am taking, and this is an important point, I am taking the hinge here, which seems to me to be the obvious place, to be 0. This FHY act.
Okay, so when you're doing the torque, you have to decide the pivot point about which to do the torque, right? Mm-hmm. Usually we just choose the leftmost point, and then therefore you don't have to worry about any torques on the other side, you know? Or you can say we choose the pivot point to be the point where there's one of the unknowns, which is we don't know FHY, FHX. So if I choose the pivot point as that, the torque due to that force is 0, right? So that's another reason why that's an obvious good choice of the pivot point. So he puts the pivot point right here, right? And then he says, okay, the torques about that pivot point must be 0, right? So then what's the torque due to the weight? You know, L over 2 mg sine of 90, right? L over 2 mg sine of 90. Plus, what's the torque due to the big mg? L mg sine of 90, right? And then the torque due to this is what? L, it's out of the board, right? So LT sine of alpha. LT sine of alpha. Oh, they actually gave you what alpha was, right? It's 35. So we know this is 35. This is 35. So what happens? The L cancels the L cancels the L. Let's see here. The sine of 90 is 1. So then what's going to happen? M, we already know that little m, right? 25 kilograms. So then it's just going to be 25 times 9.8 over 2 plus 25 times 9.8. The length of the rod didn't really matter because the L canceled for the torque, right? So then you have here T sine 35. Oh, there you have it. You can solve for the T. You can see? Well, let's see how they do it.
Acts at the hinge. There's no lever arm. These two forces, FHX, FTX, are acting at 90 degrees, and therefore there is no torque resulting from those. In the clockwise direction.
It just sounds like
Direction should write down positive FHX, Now positive FHX minus
Physics
FTX.
videos.
You should notice that there's two forces that are going to be equal in magnitude, but for as many as I can, torque is the force times the distance, the force times the lever arm, or mgd. The torque from the sine is the mass of the sine times the accelerated loop every time the lever arm. The lever arm is the distance, the force is away from the hinge, and these are all acting 90 degrees to the beam, so we don't have to use any trig signs in this. So it's just 18 times 9.8 times 2.10. It's opposite this angle, so that's the sine of 35 times the tension force. Okay, that's your trig functions. Now we're going to do the force from the sine.
Well, he's doing all the calculations of the forces.
Over FTY first. Okay? We know FTS, 370. We know the tension, the torque from hinge and the force of tension. Okay, I'm going to go over to the next slide and we're going to use the x components. Okay, once again, here's all our values.
So here's
our
how he did.
diagram,
He did
here's
it
FTY.
slightly different than how I'm doing it. He broke the tension into two components, right? And then he said the torque due to the vertical component, that's just T sine theta. So he calculated that, he got 299. In other words, he didn't get T, he got T sine of 35. And he came up with 299. So with my method, I'm gonna get T immediately, right? So if I calculate that,
I don't know if you can explain it. Like, why divided by 2 the first time?
or because the center of mass of the rod is at its middle.
Okay.
So, but the hanging mass is at the end.
Just the length from the pivot.
Okay.
Yeah, it's half the length of the rod. It's a uniform rod, you know. So 25 over 2. Run it on. Oh, I think this is wrong. Hold on. This should be 18, right? The mass of the sine is 18. So then, if you do that, you get what here? $521.1. Tension T is 521.1 newtons. But what did he get? 299, right? Well, if I do this times sine 35, what am I gonna get? 298.9, yeah, see that? So he got Ty, the y component.
Right.
So I'm just getting straight out T. Then how am I gonna get the F cosine theta? So then I'm gonna say what here? I'm gonna go to the forces. F cosine theta is, T is gonna be what? 521.1 cosine alpha, which is 35, right? And then here I'm gonna get what? F sine theta is what? Ng plus Ng minus T sine 35. So the T sine 35 is the 290, right? What was it? 298.9. So then if we do Mg plus Mg minus this, that gives you F sine theta, right? So then you just add 25 to 18, then multiply it by 9.8, right? So 25 plus 18 times 9.8 minus 298.9. 122.5. So F sine theta is 122.5. Right? Then what am I going to do? Right? If I'm more interested in the F than the theta, if the problem asks me both of them, then maybe what I'll do is I'll divide them. I'll do F sine theta is 122.5 divided by F cosine theta. Okay, yeah, this is probably the best way. And you divide them, you get tangent theta. right? Then you can solve for the theta by doing tangent inverse. Then you can put that back into there and get the f, right? But if the problem only wants to know the f, you don't have to do it this way. If they're not interested in the theta, remember the theta was the angle of the f, right? The angle of the hinge force. If they're not interested in theta, what's another way to do this? Well, we know sine squared plus cosine squared is 1, right? So we can square this, and add them. So we can say f squared cosine squared theta plus f squared sine squared theta is going to be what? 521.1 cosine squared 35 plus 122.5 squared. Then factor out the f squared. Cosine squared plus sine squared is 1. And you don't need to even solve for it. That's it. So f squared is and that's going to be the f. So let's forward this guy and see what he got here. Let's go.
X component squared plus the square root of the x component squared plus the y component squared, and you get that is 444 newtons. So the
Okay, so his answer for the tension is 521. Is that what my name was? Yeah, 521. What's his answer for that? Well, let's do this, let's do that, and then square root it, and that's the final thing. So 521.1 squared. Oh, do I need to square this? Oh yeah, I need to square the 521 also, right? I need to square this guy also.
Yeah, you get 444.
Yeah?
Yeah.
Yeah, I was gonna write to him and say, hey, you're wrong, buddy. So that's a good example of a statics problem. A beam against the wall, a ladder against the wall.
So the
Tomorrow we'll do a lab on statics too. Our whole lab is on statics and equilibrium and strength of materials.
So the whole point is like the total torque is 0.
Yeah, for statics problems.
But the
Total torque of any pivot points
all forces,
Yeah.
torque,
is 0.
X. and-
Because nothing is moving. You see, if I have this leaning on this, okay, so find the force of this on this. Find the force of the faucet on this.
Everything
Then what
cancels
is
out.
See, everything cancels out.
What is the middle one? L times mg times sine 90.
That's the
This
force
one?
at the end.
This one?
Yeah.
That's the torque due to the hanging weight. Remember? The
sine.
picture. Yeah, the point due to the sines. There's something hanging at the end.
The torque due to the
Like if I'm hanging something, that's gonna cause a torque this way.
the sine mass and then the beam mass. Beam mass 25.
There's a mass, but then there's a string pulling on it so that it doesn't fall. If there's no string, this thing is gonna just fall.
Yeah,
So you have to have a string holding it up.
Uh-huh.
but,
So that's 25.
That's how bridges are made, you
yeah,
know, these
suspension bridges.
suspension bridges.
So that's 25 times 9.8 or 18.
Whatever the mass was,
Oh,
I think
you
that
changed
it was
it.
25
Yeah.
kilograms was the hanging mass, yeah. And then the mass of the beam was 18.
Oh, the mass of being same thing.
When you do the forces, you don't care which one is what.
Yeah.
But when you do the torques, you got to be careful because
Yeah.
one is L over 2,
Right.
the other one is L. Then here I need to make sure I put the mass of the beam,
Mass of the beam.
not the hanging mass.
Right
Did
here,
I
the
do
hanging
wrong?
mass. Yeah.
What was the mass of the beam?
The mass of the beam, that's 25. Yeah.
Wait. Oh, okay, 25. No, I did it right. Yeah.
But
See, if
the-
I had put here 18
Yeah.
and I had put here 25, I
That's
get the
wrong.
wrong answer.
Right.
But
I
the middle
switch
one
it.
should be 18, right?
Yeah, I did. Yeah. See,
Okay.
25 and 18.
Alright, cool.
Okay, guys, good. See you tomorrow in the lab.